Hi, in this course on basic construction materials, this is the module on nature of materials and this is the fourth lecture in that module, and we will be looking at inorganic and organic solids. In the previous couple of lectures, we covered in this module on nature of materials, we covered electron configuration, bonding, and then lattice structure, defects in the lattice structure in different dimensions, and then we talked about the phase diagram. Today in this lecture we are going to talk about inorganic solids and organic solids, and so these are the reference books, and mainly this today's material is coming mainly from the book by Mamlauk and Zinowski, and also different photographs or sketches from the internet have been used for demonstrating various things. Now, inorganic solids, what are these? These are non-metallic elements or a combination of metallic and non-metallic elements, okay? And they are also known as ceramics, mainly because they have ionic and covalent bonds present in them. Okay. These are the two major type of bonds which you will see in these type of materials, and different classes. These inorganic solids can be divided into 5 different classes. First one is glasses, mainly based on silica, and then second one is vitreous ceramics. It is essentially like the bricks or pottery, which are essentially the clay products, and the third one is cement and concrete, again a multi-phase material with different things present inside as different phases, and rocks and minerals, and also we have some high performance material which are artificial materials to which are made to have certain performance characteristics, both in terms of mechanical and other, or in other it can say thermal characteristics, wear resistance, so many other properties are can be possible. Here are some examples shown, okay, and also they are used for machine tools. I will show some examples later. Anyway, now one problem with all these ceramic materials is in general they have poor fracture toughness, okay. And we handle that problem by doing certain by engineering the product. That is, for example, if you take cement and concrete, okay, concrete has very low toughness, or fracture toughness of plain concrete is relatively low. So, how do we handle that is by putting the steel reinforcement or steel fibers which are good in tensile behavior, in tensile properties, and then we mix them together and make it like a composite material. Essentially our reinforced concrete is a composite material, right. So, the steel rebar take care of the tensile properties required, and the concrete takes care of the compression, and also the steel reinforcement, it helps in increasing the toughness as compared to a plain concrete system. And also we have now fiber reinforced, which we discussed earlier. Different systems are available to increase the toughness. Now, classification of inorganic materials based on atomic bonds. So, they have a well defined, although more complicated, okay, unit cell structure which is repeated for the formation of crystals. So, these are just a recap on what we already discussed in previous lectures. So, you can see this is a unit cell like right here, and these are different types of unit cell that can be present in various materials. Now, in case of non-metallic materials, or we said that inorganic solids can be fully non-metallic or a combination of metallic and non-metallic materials. So, in case of non-metallic materials, predominantly you will see covalent bonds, and in case of inorganic solids with both metallic and non-metallic materials, you will mainly see ionic bonds, okay. Just a difference in terms of atomic bonding nature. Now, one example of a very good ceramic is diamond, and it has covalent bonds, like just previous slide I showed. Non-metallic means covalent bonds, right. So, the diamond is an example for that. And where do we use diamond in construction? I mean, we use diamond for cutting as cutting tools, as drilling tools, or dressing tool, or polishing tools. So, these are different types of tools which are used even in construction. So, I just want to make sure what these see, for example, this cutting tool which you see, it is not that the entire blade is made out of diamond. Okay, you have only a tip of that tool, which is, because it is very costly. So, the tip is actually made of diamond or diamond tip. For example, in this case here, this you can see these tips are made of diamond, okay, of these polishing tools. You can see all this a little bit difference at the tip, and that is what is made of diamond, and not that entire thing what you see is diamond. Okay. Now, here you have polishing tools, you have some diamond coating on this. So, you can see diamond coating. Okay. Here on the right side, drilling and cutting tool, again you have tips which are diamond tipped. Okay. So, for example, here also you will see here you will see. So, these are because it is very costly in volume wise. So, you do not want to use a lot of this material, but wherever it is required. So, the tools are targeted for that, or the some specific points on the tools where you want the tool to be very hard and at the same time strong, so that you can cut the material, and only there you put the diamond. So, diamond tips, and there also durability is very good in this case. Now, another example which we come across in construction is Portland cement concrete, okay, widely used material. It has mainly ionic bonds. So, when you talk about cement or hardened cement paste or concrete, let us say, keep it simple, because when we talk about concrete, you will know more about this thing, but at this stage I will just keep it simple as just cement or hardened cement. Okay. Now, in that you have two major complexes which are dicalcium silicate and tricalcium silicate. This 2 and S should be subscript, Tc2S and C3S, okay, subscript. Now, here C is not carbon, you note that it is cement chemistry notation, and S is SiO2, SiO2, 2 is subscript there. So, you have C and S. Now, dicalcium silicate means 2 CaO and SiO2, tricalcium silicate means 3 CaO SiO2, okay, 3 CaO SiO2. You will learn more of this in the later sections. So, 2 CaO SiO2. So, this is what that is. Now, in this ionic bond is formed between the silica and the metal oxide. Okay. So, let us look at what is the role of a silica and metal oxide here. So, this is the silica, a typical tetrahedron structure of a silica, and on the right side you can see these white circles over there and the triangle formed with a dot, that indicates the so this indicates this tetrahedron. So, this indicates this, and this indicates this. Okay. Okay. Now, that is a single element or a monomer. Okay. So, these multiple monomers will join together to form a polymer. Okay. So, what is a monomer? It is a molecule that can react together with other monomers to form a larger polymer chain or a 3D network, depending, it is not like straight line, it could grow in different directions, and a network can be formed, and this process is called polymerization. So, that happens, and then there is a bond formed between the calcium, in case of concrete I am talking, or cement paste I am talking, between the calcium here and the the metal oxide or calcium oxide and the silica monomer. So, this region you will have a ionic bond formation. Okay. So, that is a typical nature of Portland cement concrete system or Portland cement system to be precise. So, this is calcium silicate. Okay. Now, again we just discussed about the fracture toughness in the previous slide, and we know it is of much less than that of metals. It's much less means it's it could be even 1/50th of that of metal. So, it could be very low, very brittle in nature. Now, so they tend to break in a brittle manner, and like you have grain structure in metals, you also have similar structure in ceramic materials also, and stress concentrations can happen. We are looking at why this is breaking in a brittle manner. So, stress concentration can happen at grain boundaries, and also there could be internal cracks and flaws. Okay. So, these are the weak locations at which stress concentration can happen and then propagate and then leading to failure or fracture of the material. Now, let us look at an example graph here. You can look at this graph. So, this is a ceramic material, the first curve. So, you can say this is a vertical line if I draw there. So, I can say this is the area under the curve for that, right, area under the curve. And if I compare that with, let us say, high carbon steel, or let us say low carbon steel if I take. So, I have this is the area under the curve, and if I consider the area in the post elastic region, still I have very large area, and so I can definitely say that low carbon mild steel which is shown there will take much more energy before it can fracture into two pieces. So, area under the curve of ceramic is much less than that below the low carbon mild steel. So, like this you can take a stress strain curves and then find out what is the fracture toughness or the energy required to break the material. Now, crystalline and non-crystalline structure. So, ceramic materials can in general have two, maybe more, we will see a third one later, but in general we say crystalline and non-crystalline, okay, structure. And this non-crystalline is also known as amorphous. This is that usually you will see this word amorphous when you read articles. Now, crystalline, when we say they are ordered in longer range. So, look at the first picture on the first sketch below. You can see that this entire the picture or entire sketch here is kind of in a well ordered manner. Okay. Whereas, if I look on the right one, I see not really an ordered structure. So, that is more of an amorphous or a non-crystalline structure. Now, both these, you see those two circles, red circles over there. So, both these are formed with monomers like this one and this one. Okay. You can see monomers like a same type of building blocks are still there. Okay. In both these left and right, quartz and glass, you have the same monomers present, but when they are arranged in a in a larger volume, in the quartz case you have a very good very well structured, in the long range means larger volume is in a proper structure or in an ordered manner, whereas in the case of glass, that orderness is only for a very short range, it is not for the entire or the larger volume. Okay. So, that is what we mean by long range and short range, or you can say large volume and small volume. So, here in the second case it is not well structured, and so we can call it either non-crystalline or amorphous in nature, and you will hear this term in many classes in future. So, it is important to understand what these means. Now, there is also one which is in between these two, which we can call polycrystalline. Okay. So, you can see here crystalline structure, on the right side you have non-crystalline, and now in the middle somewhere in between you have polycrystalline structure. So, you can see here in this polycrystalline, this is one crystal pattern, and this is the another one. Okay. So, you have two crystal structures shown there. So, polycrystalline. Now, that is about the inorganic solids. Now, we will talk about the organic solids. Now, these are long molecules of covalent bonded carbon atoms, and these are chains. These molecules are, like you can see in the picture at the bottom, you have a polymer, I am going to call it a blue color, and then polymer 2 which is green color. Okay. So, these molecules are chains of carbon and hydrogen combined with various radicals, okay, or functional groups, that is another term. And for example, functional groups such as hydrogen or hydrocarbons can be cross linked with covalent bonds. Now, you can see here closely. So, I have this blue, this is one polymer chain, and then this green one is another polymer chain. Okay. Now, when they are combined, so you have a covalent bond formed here. So, this you have a radical on the radical 1 or radical 2 or functional group 1 and 2, and that will combine to form a covalent bond, as you see here in the second case. Now, we can call this also as a cross linker. Okay. So, this presence of these cross links changes the behavior of the material. So, in the future slides you will see how important these cross links are. Even in some of the advertisements you can hear, like when you talk about paint, cross linking polymers are used in paint. So, that helps them preventing cracking of the paint. So, in the wall surface you will not see much of cracking, because they have this cross linking polymers, and which changes their elastic behavior a little bit, or their it takes more deformation for that to crack. So, these chains or cross linking chains, they help in changing the properties of the material itself. Now, in general, the organic solids can be classified into thermoplastics, thermosets, elastomers or rubbers, and natural materials. Natural material I am not going to discuss too much detail here, because it is mainly wood or even asphalt for that matter. You can say crude oil, in the processing to which level it is processed, because it is essentially a naturally available material, even though you do have some processing there. So, wood is a very good example of natural material which we use in construction. Now, we will discuss these three in the coming slides. So, before we go into the coming slide, let me just briefly explain what the major difference between these three could be or are. So, you can see the thermoplastic, you have this different, all this you can see like one chain which goes something like, let me just do it again. You can see that there is one chain which is starting here, it goes like this, and then this is one chain. Another chain, if I want to track, could be, it comes like this, and it goes like this, it goes like this, it goes like this, that is another chain. And another chain, you can maybe plan this one you can consider as another. So, there are multiple chains in this structure, okay, and they are not really connected to each other. That's the main thing to notice there. They are not really connected to each other. In case of elastomer, you can see there is one chain, another chain, another chain, and there are also some cross linking happening in between, but that is of similar nature material. It's And now thermoset, you can see there are multiple chains and they are really cross linked a lot. Okay, so they are really cross linked. So this is the major difference between these three groups of materials: thermoplasts, thermosets and elastomers. Now we will look a little bit more detail into these. Thermoplastics, as I already mentioned, these have linear carbon chains, okay, that are not cross linked. So you will not, it is not cross linked, that is the main thing. So they are just linear carbon chains. Okay, follow one this and maybe another one. I mean, you can try which drawing belongs to which chain. So anyway, there are multiple linear carbon chains which are not cross linked. Okay. Now what happens is, when the temperature is relatively low, the secondary bonds, they adhere the chains. Okay. But upon a little bit of heating, what will happen is these secondary bonds can break, okay, and the material becomes viscous. They tend to flow, or they starts flowing, and then so this is a good thing in when we talk about reuse of materials. We can actually use the same thermoplastic material, melt it and then reform into a different shape. Okay, so we can reuse. So in terms of sustainability, this will be a good type of products to use, because we can increase the reusability of this material. These are some of the examples of thermoplastics. You can see polyethylene, we use a lot of these in various pipes. Polypropylene also we use. So you will see that many of our construction sites, we will have a lot of these plastic materials being used. These are some of the for electrical wiring, or some containers, different type of materials which we see in our day to day life. We use all these materials a lot. Plastic is probably not it's not our, we cannot live without plastic. I think today it has reached to that level. Everywhere we use it, but what we have to see is, because they have very high carbon footprint, all these materials. So we have to see how to minimize or probably reuse these materials as much as possible. Now polytetrafluoroethylene, this is also known as Teflon, which is widely probably known to you. We know that they have been used for this non-stick cookingware at home, but one important use which is in terms of construction is we use that for gaskets or sealing, etc., because they have very good adhesion property and very good heat resistance. That is why it is used for cookware, but main thing is low friction and adhesion, and so it is very widely used for making watertight connections, etc., in pipes. You will see that in future, or whenever you see go to the site, etc., you will see where Teflon tapes are being used when you put two pipes together, and coupling in between the threading, you will provide that. Okay. Now other example is polystyrene, which is very widely used for molded objects, and PVC full name is polyvinyl chloride, and it is used for water pipeline, electrical conduits. I am just citing couple of examples here, but you will see that most of these materials are used in variety of products, and nowadays it is becoming more of a general purpose plastics. Many places you will see different plastic forms, even pipes which you see. There are other types of products also, not only what is shown in this paper, in this slide. So PVC pipes, these are also some heavy duty pressure pipes. On the one on the right side, you can see the thickness is very high, so it can be also used for some pressure hoses. Of course, there will be limitations on that. Sometimes we also reinforce the pipes with some fibers embedded inside the wall of the pipe. So there are different applications, and tailor made products will definitely be there. Now other set of plastics are thermosets. usually made with a resin and a hardener. Okay, a resin and a hardener. What they do is when they are mixed together, they chemically react and then harden to whatever the shape we are putting it in. Now, when I say chemically react, you can see how it is used is, you can see, maybe before that I will just explain what they are. Carbon chains are cross linked to form stable compounds that do not soften upon heating. In case of thermoplastics, we saw that when they get heated, then your chains are the secondary bonds are broken and then it starts flowing, right, or the viscosity decreases. But in this case what happens is it does not really change its viscosity, and this is very stable products are formed in case of thermosets. So, you can see here there are a lot of cross links here, so which are probably very difficult or they need higher energy level to to break them. Examples are epoxy and polyester. Epoxy is widely used as glue. This is one example. As you can see here, this is a glue which is widely used in construction. You can see there are two tubes connected, and what we do is we press these two together with our fingers, and it is like a syringe. So, equal amount of material comes out of the two syringes which you see, 1 and 2. Okay. And so, equal amount comes out and then you mix it. So, one is resin and the other one is hardener, and then you mix it very well, so that the 50-50 combination, part 1 part 2 or part A part B, like that they would be mentioned in the products, and you mix them, and then once you mix it, they react and then form a solid stable compound which cannot be which is very stable and then will not change its properties so easily upon heating, and you can't really melt it and regain the shape also. That is the one disadvantage of thermosets. Okay. And these are also used for as reinforcing phase. You can see here in fiberglass, you can see here some fibers over here. They are polyester fibers which are kind of spread and functions like reinforcing material when we talk about fiberglass sheets, or even the car body. If you look carefully, you will see that there are some fibers in that, and that is sometimes fiberglass is used. I mean, there could be other products also, but I am talking about first generation products which were used for car body. Once the metals, people stopped using metals, they started using fiberglass. So, this is one use of fiberglass. In construction, definitely we use that for different type of sheets which are in. So, in this picture it may not be very clear, but you will have small fibers in all these. If you look carefully next time when you see a transparent or any roofing material, you might probably see that there are some fibers present inside, like a composite behavior it gives. So, fiberglass provides that tensile strength or the toughness which is required, whereas the remaining material usually provides the volume and then make sure that it has a definite shape also. Okay. Now, another material which again comes in the category of organic solids is elastomers. Okay. Now, again these are linear polymers, okay, like the earlier we talked about this one, thermoplastics. Okay. Now, they have, in case of thermoplastics, they did not have cross linking chains, but here they do have, but very limited. Okay. So, you can see here, one here, one here, one here, very limited cross linking. And now, the secondary bonds which are present melt at atmospheric temperature, and then cross linking, the presence of this limited amount of cross linking chains enables the material to behave in an elastic manner. Okay. So, what does it mean? When I say behaves in an elastic manner, means when I pull it, it will try to come back to its original shape when it is the load is removed or when it is unloaded. Now, For example, if I say this particular thing, if I pull here and here, some of these cross links will kind of realign themselves until it becomes stretched, okay, and when I remove the load, it will come back again to the original shape. Okay. So, that is what it means, how these chains help. Okay. So, I can probably show, let us say this is something like this chain is like this. So, I put this force here, then what happens is it will kind of become something like this. So, these chains will kind of rearrange. Okay. So, when they rearrange, it will elongate, and when I apply the force, it will take this shape. When I release the force, it will come back to this original shape. So, if I am going to call this as first and this as second case. So, when you apply the load, before application of the load, the structure is like in 1, that is here. When you apply the load, the structure becomes something like this in 2, and then when you release the load, again those cross chains will come back to its original shape, which is like in 1. So, you have an elastic behavior. What are the examples for this? You have natural rubber and then you have synthetic rubber. Now, we have a lot of sports complexes and many applications where synthetic rubber is used. Okay. And then also major application in construction is when you talk about bridges. Okay. Now, there are some changes in that, but there are a lot of bridges where these type of neoprene pads are used. So, you can see this bridge here. So, what I am talking is this point here. Okay. The girder which is on the top, the actual bridge element or the girder is resting on the columns or pillars. So, where they are touching each other, that is where you provide a rubber or this neoprene pads. Okay. So, you can see this black piece here is what I am talking about. So, they put this neoprene pad so that there is a proper load transfer happening from or kind of shock absorber. It is not that proper load transfer, you kind of dissipate some of the energy because of this shoe, so that the columns some of the vibratory load which is coming from the girders do not get transferred to the column. So, anyway, they provide good necessary energy dissipation over there, and then help the bridge to function the way it needs to function. And there are also a lot of other products which are made of these elastomers. Now, in all these organic solids we have, or the solids which we are talking now, ceramic materials, we have melting and glass transition temperatures. Two properties which I just want to talk about. One is melting. Let us first look at that. So, the reaction of polymers to temperature, we have seen that when temperature changes, the cross link breaks or it moves or it gets elongated and it behaves, the material behaves in a different way. So, the reaction of all these polymers to temperature depends on the degree of crystallization. Okay, how well the crystal structure is, and that is how that will influence the relationship between temperature and the behavior of the polymers. Now, highly ordered polymers have a fairly well defined transition between elastic and viscous behavior. Now, if I look at here, you can see this graph A where I am talking about melting point Tm. So, you can see that when it reaches here, very well defined melting point. Okay. Now, this is a case with highly ordered polymer melting point. You can very clearly see that at this particular point the volume increases significantly. That means the material starts melting, and when it starts melting means what happens is, when the temperature increases, there are molecular vibrations, and because of those vibrations they tend to get separated, creating some volume in between, or they tend to get separated and occupy larger volume. Okay. Now, what is this larger volume? That is what we are calling as free volume. Now, let me go to the next slide where upon cooling what happens. So, that was about the melting point, and upon cooling the motion of the molecules decreases and the viscosity increases, or in other words, the material, it becomes more and more difficult for the material to continue to flow. Okay. So, the viscosity increases. So, we are going backward direction. Now, at sufficiently low temperature, the molecules are no longer free to rearrange and their positions are fixed, and when their positions are fixed and there is no further volumetric expansion or volume change possible. So, we can call free volume becomes 0. Okay. So, here what is this free volume? It is you can look at that drawing at the bottom right. So, that free volume becomes 0, and that temperature is what we call as glass transition temperature. So, I am talking about this point here. Okay. So, at this point the free volume is 0. Now, below the glass transition temperature, what happens is the secondary bonds bind the materials together and it can become an amorphous solid. Okay. Now, above the glass transition temperature, the material behaves in an elastic manner. Okay. So, it also depends on what type of bonds are present. Now, for an example, acrylic is the plexiglass or the glass like transparent sheet which we use in construction. You might have seen it is not glass, but most of it is we call it acrylic, and it is a transparent sheet widely used in construction where you do not want glass, but at the same time you want transparency. Now, its glass transition temperature is 100 degrees Celsius and above the glass transition temperature. So, if you take that sheet and then you start heating it, after about 100 degrees Celsius, you will see that the material starts to flow. It becomes leathery or rubbery, starts to flow, and then its properties can change, even the mechanical properties will change. So, I will show you how the mechanical properties of various polymers change, and they are definitely dependent on the degree of orientation of the molecules or the crystal structure and the amount of cross linking. Both these are influencing the mechanical properties of the polymers. Here is an example graph which kind of compares various materials and their elastic modulus. So, you can look at here fraction of covalent bonds, or how much of all the bonds which are present, how much is the covalent bonds. So, you can see as you have very little covalent bonds, the modulus is very little. On the bottom left corner region is what I am talking. As the amount of covalent bond increases or the fraction of covalent bond increases, the modulus is also increasing. So, for example, the plexiglass or the acrylic which we just talked about, the modulus is somewhere here. Okay. So, I can say the modulus, this is log scale. So, you should note that. Okay. The modulus is somewhat here. So, maybe that is about 2 or 3. Okay. Let us say 2 or 3. Now, if I take cross-linked polymer or epoxy materials, okay, that is thermoset plastics, I can probably see that this is about here, maybe 6 or 7, something like that, or this will be about 5, I think. Okay. Now, if I look at the other type of manufactured products, very high performance material, then I am seeing like it goes even this could be about 50 in the log scale. Okay. So, you see from 5 it is about a 10 times increase from here to here. Okay. Now, it is not only 50, you have also very high about 100. Okay. This could be close to 100. Now, when you have 100% covalent bond, you have very high modulus. Okay. For concrete, for example, you have very high elastic, concrete also depends on what type of concrete you talk, but if you have, or 100% covalent bond is diamond, you have very high modulus for the diamond. So, it depends on different materials. So, definitely these bonds do play a role in influencing the mechanical and other properties of the of various materials. So, definitely they have a huge role in designing our structures and making sure we understand those behavior at the microstructure level, so that we will be able to design and incorporate those in our civil engineering design, and then ensure that our structures stand safe for the structure and for the users for the desired life, that is service life. And we talked about a lot of these in the earlier lectures. Service life, sustainability, all these words were introduced to you. So, please read all those concepts. It is very, very important in today's world for us to incorporate these concepts in all the designs which we talk about. Not all the structures which we design should not only last for the initial few years or something, but it should really last for long time. So, you have to decide what is that design life, and then when you choose a particular material, is that going to really give you the long life which you are desiring for the structure. For example, I did not talk about it earlier, but let me just tell you, most of the plastics which we talk about, if it is used for external or exterior environment where sunlight is going to directly hit the material, you have to really think about the UV radiation, whether this plastic will degrade in short period of time. So, that is something which is very, very important for us to think about when we use plastics. If it is going to be covered, then it might be okay, it might last longer, but if you are going to use it for exterior environment where it is directly hit by sunlight, etc., you will see that if it is not UV resistant, they will become brittle very fast, and it may not be good for the structure. I think to summarize, we talked about inorganic solids, organic solids, in which we talked about thermoplastic, thermosets and elastomers, and also towards the end we talked about properties of polymers, how the very briefly how the bond can influence the properties and how it is related to the temperature of the ambient temperature of the system. I think with that we will close this session, but before we close, I just wanted to tell you there is something called Bloom's taxonomy. So, these are, you can read about it, it is not part of the syllabus as such, but I thought it is good because some of you may be interested in becoming teachers. So, it will help in how to set question papers, etc. So, this is a way of distinguishing the fundamental questions within the education system. So, you can look at this table, all these words which you see, you will see them in various questions in the exams, okay, and in our class also we will try to use So, this helps us in identifying the depth of knowledge a particular student has. So, for example, if we use these kind of words in the question, that kind of just checks whether the student remembers something or not, okay. And if you have compute something, convert, defend, discuss, all these words, estimate, this checks whether they understand the concepts or not. Third one is to check whether they can apply a particular concept or not, and then fourth is analyze, then evaluate, then create new knowledge, or it's categorize, so creating something. So, these you can, I do not want to talk too detail, you can look at all these words and then you can see how to use these words in your question paper, especially if you see them, as you go towards the right, that is more and more difficulty level kind of increases, which is shown in the triangle over here, where you can see first one is recall, just memory checking, and then second one is understanding all that, then third one is using and applying knowledge, identifying and analyzing patterns, using all concept to create new ideas, and then finally assessing theory. All this is for evaluation. So, as you go up, it becomes more and more difficult. So, just wanted to introduce this concept called Bloom's taxonomy. You can Google on this and learn about this also, especially if somebody is interested in becoming a teacher in future. Thank you.